Welcome everyone. Today we are going to talk about Oppenheimer and Snyder, gravitational collapse and black hole formation. Before we go to Snyder paper, let us talk about what Chandrasekhar did. Now, when people looked into the sky, they saw something called white dwarfs. There are a lot of them out there. They're not as bright as our sun, but they're very small. They're like the size of a city, and they're extremely dense, and they have the mass of similar to a star. And it occurred to the astronomers, these are dead stars. Now what happens is when a star dies, when a star dies, the gravity would act towards the center, and at the center there are electrons. Like if you take two atoms, and then at the center you have center of atom, at the center of the star. Center of an atom you have the nucleus, protons and neutrons, and then you have the electron cloud. And when two atoms start coming together, there would be a repulsive force. And then there are a whole lot of atoms at the center of a star, and that repulsive force would keep the gravity from collapsing all the way. And then that's a white dwarf situation. But what Chandrasekhar showed was that if the mass of the star is more than 1.4 times the mass of our sun, this repulsive force that exists between electron or electron clouds is not enough to hold back gravity, and it would keep collapsing beyond the white dwarf state. And what would happen now? So the electron get compressed into the protons and create a neutron, and then you have a ball of whole neutrons after that, and that's called a neutron star. So it's like this. Now we have a neutron star at the center, and the gravity is acting downwards. Neutrons, this big core, will have a repulsive force to hold the gravity. Now what Oppenheimer and Snyder asked, what if the mass of the star is even bigger? Then this core is going to be able to hold back gravity, or it's going to collapse. And then if it's collapsed, where is it going to collapse? And that was the question that Oppenheimer and Snyder asked. So what they did was first I would read what he said in 1939 paper, when this is from the Oppenheimer and Snyder paper. When all thermonuclear sources of energy are exhausted, a sufficiently heavy star will collapse. Unless fission due to rotation, the radiation of mass, or the blowing off mass by radiation reduce the star's mass to the order of that of our sun, this contraction will continue indefinitely. But what they're saying is, when the mass is bigger of a star, then beyond more than 1.4, it will collapse beyond the white dwarf stage. That's what the Chandrasekhar said. Now, even if the mass is even bigger, then it would collapse to this state where electrons and protons got crushed together, and that's a neutron star, not a white dwarf anymore. And Oppenheimer and Snyder checked, if the mass is even bigger, then this would also collapse. So we just want to know how they did it. So we have, now this is called the Oppenheimer and Snyder metric. ds squared equals E nu dt squared minus E lambda dr squared minus r squared d theta squared. And so what are these? D squared is the distance between 2 points. That is the metric. And E nu is 1 minus r naught over r. And r0 is the Schwarzschild radius, that is the mass of the star, and the c is the velocity of light, and the r is the radius at any given time, and E lambda is this, and this is R0, m is the mass of the star, and RB is the radius of the boundary of the star, that is obvious. R is radius at any point, m is the mass of the star, and so this is the metric. So theta and phi are basically the coordinates. It's a spherical coordinate angles. So this is the metric. So how would you derive a metric? Now you have Einstein's field equation. R nu is the Ricci tensor that could be written down using the metric, and R is the Ricci scalar that also can be written down, and G nu mu is the metric. This is the metric, and this is R can be written down using the metric, and this is the cosmological constant that does not come into play unless you are talking about billion light years or so. Even between galaxies, if you are doing any computation, this does not come into play. So this side gives the curvature. So this number is 0 for our purposes. As I said, this would be important if you are talking billion light years or more for the whole universe. So this value is the curvature we can get from the metric, and the Christoffel symbol also can be obtained using the metric. So if we know the metric, we can solve the curvature, but the metric is related to the energy flow. So the energy flow is a tensor, and the energy flow for the outside of a star was done by Schwarzschild. Now Oppenheimer and Snyder did the energy flow inside of a star, and then they tried to find the curvature, and that's where things got pretty crazy. And if I gave this example before, I'll give it again. Let's say Einstein's field equation. Let's say we have this hexagon, and we don't know how to calculate the area of the hexagon. And then somebody says, well, if you know the sides, I have an equation. This is the equation, I could use it. But how to find the side? Then you have to measure it. To measure, a ruler is needed. So it's like that. So Einstein field equation is like the area of a hexagon, and we need a ruler to measure, and that ruler is the metric, and that metric is dependent upon the energy flow of the situation that we are considering. And Schwarzschild considered a condition outside of a star, how planets would move outside of a star, and Oppenheimer Snyder considered inside of a star. So, and they derived their own metric, and that metric is this, and the Schwarzschild metric is different than this one. And then once you have the metric, then you could solve Einstein's field equations and find the curvature, and the curvature became infinite, and the volume and became 0, and that's called the singularity. And this is the first time that people were confused. Could this singularity or black hole exist? And they found also how long it would take to collapse. The total time, this is from the Oppenheimer and Snyder paper, the total time of collapse for an observer co-moving with the stellar matter is finite. Now, what is co-moving means? Co-moving means like if you take two particles at the boundary, outside the observer, look at them and see them moving towards the center. So that is, the two particles are co-moving, and for an outside observer, and his time is t. And for these two people, if there are observers in this frame, and their time is proper time. And what Snyder, Oppenheimer and Snyder is saying, the total time of collapse for an observer co-moving with the stellar matter is finite. So if there are observers, they would come to the singularity in a finite time. And for this idealized case, typical stellar masses of the order of a day. So within a day, this star would collapse to singularity. Within a day. But an external observer sees the star asymptotically shrink into its gravitational radius. But someone looking from outside, this will never end. These people are there. They just keep moving very, very slowly. So this is another problem. And now, this was it is fair to say that this was the very first paper that we could say that the black hole idea was theoretically presented. Chandrasekhar's paper gave way for people to think in a new way, like what would happen if the mass is more than 1.4 times, then the electron soup is not, electron repulsion force is not enough. And Oppenheimer and Snyder went further and showed that if the mass is more than 2 or 3 times bigger than our sun, this thing is going to collapse indefinitely to zero, and that's called the black hole. And the black holes today are a reality. Photos have been taken, and everybody believes in black holes today. So thanks a lot for listening.